Welcome back. In this video, we look at decision trees, a highly interpretable algorithm that can be used for classification or regression. Decision trees recursively split the input observations into partitions until the observations in a given partition are uniform. These regions will be rectangular in 2 dimensions as seen in this figure, and cuboid in higher dimensions. Notice that the decision boundaries are linear and align with the axes. The algorithm is greedy and does not go back and reconsider earlier splits. Once the vertical split at about 125 is made in the figure, the only consideration at that point is whether or not to further divide the regions to the right and to the left. Decision trees are not among the highest performing algorithms, but they have the advantage that they are highly interpretable and give insight into the data. Let's look at a decision tree in R. There are many packages for decision trees in R, including rpart and tree. This notebook looks at both. First, library rpart. Using the iris data, we want to model species as a function of all other predictors on the entire data set, and we say method equals class so it knows we're doing classification. If we look at the tree, we get a lot of information here about how it made its decisions. But we can also plot the tree. How to read the tree, although it's a little difficult to read here, is that the first split it made was petal length less than 2.45. So that means on the left branch it's true, on the right branch that's not true. And then it made one more split. Petal width less than 1.75, down here is versicolor, and if it's not, it must be virginica. Now we look at what the tree function did on the same data. It made a much more complex tree. It made the same first initial split of petal length less than 2.45, setosa, the same second split, but then it went on to further splits. So the interesting thing about some of these further splits is that it made an additional split, but both leaves are virginica. So you might wonder why it did that. Well, one of those leaves may be more pure than the other one. If we type the tree name into console, we get a little additional information here. The number of observations, and then for each split, it tells us how it split them. So the first split here, it put 50 in the setosa branch. And you see the loss and the probabilities here. And you can kind of read this. If you tilt your head to the left, this would be kind of the tree structure you show with the indent levels. As we just saw in R, all observations start in one leaf, one giant region, and then the algorithm recursively splits the observations. If it chooses a qualitative feature, it would split by levels. A binary feature would easily split left and right. If there are more than one levels, then one level would be on the left and the others on the right. For quantitative features, it has to determine a cutoff point. And this recursive splitting is repeated until all observations in a leaf are similar. There are many different metrics that decision tree algorithms can use to find the best split. First, we'll talk about entropy and information gain. Entropy is a measure of uncertainty or chaos in the data. The formula there sums for all the probabilities of our classes, the probability times the log of the probability, sums those up and negates it. H is the traditional symbol for entropy. So we notice in the plot of entropy that at 0.5 here, we would have the highest entropy of 1. Entropy ranges from 0 to 1. And if you have two classes with equal probability of 0.5, then that's the most chaos in the data. The data is not homogeneous. And the more towards you get either lower probabilities for a given class or higher, the lower the entropy. To make this more concrete, we'll look at entropy in a toy dataset. This is the tennis dataset, which for 14 days recorded whether or not we played tennis, and also different predictors of outlook, temperature, humidity, and wind. So simply by counting, we see that there were 9 days when we did play and 5 that we didn't. So plugging those numbers into the entropy formula to get the entropy of the entire data set, our first probability is 9 of 14, and our second one is 5 of 14, and multiplying that out, we get a value fairly close to 1 of 0.94. So this data set has high entropy. Next, the algorithm needs to decide where to split. So it will look at each predictor. Let's look at wind equals weak. There are 6 examples where we play and 2 where we don't. So calculating the entropy of this one predictor at this one level, wind equal weak, we would get the probability of 6.8 and 2.8 and plug those in, and we see that the entropy of that predictor at that level is 0.811. Wind has another level, wind equals strong, and there are 3 days we played and 3 we didn't. Well, that would give a probability of 0.5, so we know the entropy is 1. Now we need a way to decide which predictor is better. And the metric used with entropy is information gain. It's going to measure the reduction in entropy. So we want to look for a split with a high information gain. What we do is take the initial entropy and then subtract the entropy of the proposed split, scaled by the number of observations in that split. The information gain for a split on wind would take the entropy of the data, which was 0.94, and then it would subtract the entropy of at one level, which was 0.811, scaled by the number of observations in that level, times the other entropy, scaled by the number of observations at that level. And we see we get a very low information gain of 0.048. Another metric that's sometimes used is the Gini index. So Gini measures homogeneity, or leaf purity. In this metric, we want a minimal score. There are many variations of this formula. The formula I'm going to use is 1 minus the sum of all the probabilities squared. So to look at the Gini index of the tennis data set, that would be 1 minus 9/14 squared minus 5/14 squared, because there's 9 days we played and 5 days we didn't. And that would give us a Gini index of 0.459. Let's look at a decision tree regression example. We're going to do regression on the Boston housing data. First, as a baseline, we'll perform linear regression. We see we got a correlation of 0.8045 and a root mean squared error of 0.5366, which in this data set means that we were off about $5,366 predicting the home price. Let's build a tree, and you see it's quite complex, particularly over here. It created quite a bit of levels. What we sometimes want to do is prune the tree. The idea is that if we prune the tree, it might not overfit. Decision trees do have a tendency to overfit, and therefore it might generalize better to the test data. And even if it doesn't perform better on the test data, it will be more interpretable than this complex tree. So we can use a cross-validation built in, cv.tree, to help determine where the optimal point is to prune the tree. It's a little hard to see an elbow here, but I chose 5. Then using prune.tree, I told it I wanted 5 leaves remaining. So we have 1, 2, 3, 4, 5 leaves. And we can see that this tree is now highly interpretable. Lower stat homes go over here, rooms less than 7.5 go here. And you can see that because this is a regression tree, what we have at each leaf level is the average of the target value for the observations in that leaf. When we pruned the tree, the correlation was very slightly higher than for linear regression, and the root mean squared error was slightly lower. So this got slightly better results than the linear regression model. I mentioned earlier that decision trees are highly interpretable, which is their advantage, but they're not the best performing algorithm. Decision trees suffer from high variance. One way to counteract that high variance is with a random forest. A random forest generates multiple trees. In this case, we see that it made 500 trees. And then it will aggregate the best model from among those 500 trees. The random forest will significantly outperform the decision tree, but at the cost of losing that interpretability. What the random forest does, in addition to generating many trees, is to randomly try a subset of variables at each split. This decorrelates the trees. Because the decision tree is a greedy algorithm, there may be one predictor that appears to be the best and is always selected first. However, considering all the possible splits as a whole, it may not actually be the best first split. The random forest can overcome that strong predictor. We set this parameter importance equal true to ask it to consider variable importance also as it splits. When we predict on the random forest, we see that it got a correlation of 0.93 and a root mean squared error went all the way down to 3.435. A related concept is bagging, which is a bootstrap aggregation method, and we specify that here by telling it we want it to use all the predictors. It gets comparable performance to the random forest, as we see here. Random forest had a very slightly higher correlation than the bagging, and also a very slightly lower root mean squared error. Linear models will outperform decision trees if the underlying data is more linear. But if the data is complex, decision trees have a good chance of outperforming the linear models. Decision trees are considered to be non-parametric algorithms. We're not learning any coefficients about the data. An advantage of decision trees is that they're highly interpretable, and the disadvantage is it has very high variance. It's sensitive to slight variations in the data. Pruning may help a tree not overfit the data and will also make the tree more interpretable. The high variance of decision trees can be overcome with bagging, bootstrap aggregation, or random forest, which make hundreds of trees and aggregate the results to form the optimal model of the data. These approaches are much more accurate, but you lose that interpretability. Random forest has the additional advantage of only considering a subset of predictors at each split, which decorrelates the trees. Random forest is a highly accurate model and consequently very popular as well. The end of the chapter has a quick reference for how to build a decision tree, as well as plot it, and how to make predictions. Notice that you need to remove this type equal class if you're doing regression. Also, how to do cross-validation and pruning, and how to do either bagging or random forest.